So we have the mathematical tools ready to speak about conservation laws in continuum systems. We will start with a very simple case of one-dimensional conservation law. So we have the simplest possible system, one-dimensional system that doesn't move. So it's a fixed interval AB. It has some conserved quantity, which we call by A, a source term denoted by B, and on the boundary a flow term denoted by C. In continuum mechanical contexts, we typically give the conserved quantity and source term for mass unit, which means that we also need the mass density, which we denote by rho, because we are making sort of integrals in the length scale, so to get mass integrals, we need the density. The conservation principle was that the rate of change is equal to the difference of source and sink and difference of inflow and outflow. So we have the system state, the whole state, its rate of change by time derivative. B is the difference of source and sink. So it can be both positive or negative. So it's the source term in the volume and then the boundary term. So flow on one boundary, another boundary. So and this should be valid not only for the full system but for arbitrary subsystems. So for any subinterval, and if you repeat that process to the limit, you will conclude that eventually you have to have pointwise this relation. So the pointwise change of state or rate of change of state is equal to the pointwise source term and pointwise derivative or gradient of the flow term. So this is the source term. This is the difference of incoming and outgoing flux through the boundaries of the infinitesimal environment of the actual point. So this is how the conservation law looks like in mathematical terms in simple steady system that's not moving around. Actual systems move around. So if the system moves, deforms, means that the density can move and can change. A and B are functions of time, so they also move around. So we get the law in more complicated form because we have to express the time dependencies and space dependencies of all variables. Now, if you look at this, so we have to differentiate inside the integral, but we also have to differentiate on the endpoints of the integral. And knowing that the endpoints are moving with the velocity, so the time derivative of at is the velocity at a, we will eventually get for the rate of change this term. So this is the term we learned about on previous slide, so for immobile system, and then for moving system we have this term that is extra. So the general case for one-dimensional conservation law is like this. So we have rate of change pointwise, something related to moving of the system, source term, and flow term. We will return to this once again in 3 dimensions, or in higher dimensions in general. So then the change of state has the same structure. It has the pointwise term and something related to the movement of the system, velocity and density and so on. Source term is pointwise. It's still easy. And the flow term is now written a bit differently because the boundary is now more complex than just 2 points. We see something that is very, very close. Okay, this is the actual boundary term, and we will change it by Gauss formula to this volume integral. And once this is done, we get the 3-dimensional conservation law, generic ones. So we have the conserved quantity, the pointwise dependence component from the deformation, source term, and the flow term on the boundary transported inside the system. So now we are ready to speak about some continuum mechanics using the tools that we have been using. When speaking of continuum mechanical conservation laws, it's customary to start with the conservation of mass, which is the most simple one, and works as the basis for other elaborations. So, for conservation of mass, in a simple situation where we have only one substance to be modeled in the system, the conserved quantity in this formalism is sort of trivial. It's 1. So it basically says that mass will stay as a mass. So the whole density will be sort of representing the same mass. And the conservation law is very simple. It only contains the pointwise change of density and the term due to deformation of the body. As this is so simple, let's discuss briefly what happens if we have a more complex system. So if we have a system where we have several substances to model, for example, we have maybe some liquid with diluted substances with different concentrations, maybe ongoing chemical reactions and so on. We have to write the law for each substance having a partial density, partial concentration, or concentration as a partial density. If this is the case, we have several partial densities, and their proportions are the conserved quantities. The volume terms will appear if the substances undergo chemical reactions. So maybe 2 substances are consumed to produce third one, or vice versa. And as the substances react, they also, or even if they don't react, they can move around in relative motion. So some substances will move around compared to the average flow of the whole system, and there's some system internal diffusion, and that will be modeled by the flow term. But this goes a bit deeper than we will discuss during this lecture, but it's something to be aware of when making models of more complex situations. The second conservation law is the conservation of momentum. Here in our formalism, the conserved quantity is the velocity. Momentum is mass time velocity, and because the mass was modeled by the density in our formalism, the actual A in our form is V, but it gives the conserved quantity to change, to follow the changes rho V, which is basically mass times velocity, so the momentum. The source term we denote by G, because this is the external force that applies for a mass. So this, and that is, in our case, is gravitation. So gravitation can act directly to the mass without operating through the system boundary. So it creates a volumetric source term that will create the force and change the momentum of the system. And then we have the flow term. So the flow of momentum through the system boundary is modeled by concept called stress tensor, which we denote by tau. Okay, in 1D everything is sort of simple. It's a variable whose derivative enters to the system. But in higher dimensions, tau is a higher dimensional object. It's a two-dimensional tensor or matrix that will tell something about the forces that apply on the system boundary. We will not go too deeply to that now. There's another conservation law of momentum, which is the conservation law of angular momentum, which is focusing on the rotational movement of the material. So if the system is not moving around globally, but just rotating around itself, there can be significant angular momentum even if there's no momentum in the sense of this law. In 1D, this makes no sense, because in 1D you can't turn around. In 2D, 3D, things are different in this respect. So the law of angular momentum can be written mimicking the law of conservation of momentum, just by replacing everything by thing cross x, where x is a cross product and x is the space variable. So this sort of tells the distance to the, say, axis of rotation. Okay, this law is independent on the choice of coordinates to the space variable. But we will skip this law very, very briefly, or very fast. Then there's one more conservation law to discuss about, which is the conservation of energy. Here, the conserved quantity has component E, which is component of internal energy, and then it has a component of mechanical energy. So it's the energy of the movement So mass time velocity squared divided by 2. So the energy related to the motion. So it's from the mechanical part, from the conservation of momentum part, sort of. And E is something that basically doesn't inherently have anything to do with system movement. So it's system internal energy that is there irrespective of the movement of the system. For the source terms, we have a similar division. We have the energy source that is due to basically movement in the gravitation field. So this is what you do where you gain potential energy or you lose potential energy by moving in the gravitation field. And then you have an internal energy source. So you are bringing in or taking out energy inside the body by some mechanism that is not modeled in your model. So basically often you make a simplification, so you ignore maybe some chemical reactions that produce energy and so on. So you have something that you model as an internal energy source. And finally, you have energy flow on the boundary. Well, once again, you have the force that is applied on the boundary. So it's the pushing energy to the system. And you have energy flow, which is basically the flow of internal energy. So these are the components. You will fill in to the general template and get the complex formula. Luckily, if you apply systematically the law of conservation of mass and conservation of momentum, this will simplify rather substantially. And in 1D formulation, you get something which has basically the rate of change of internal energy. You have the source term of internal energy source. You have the energy flow term. So these are the new terms coming from the sort of conservation of energy. So these components. And then you have something that links the stresses, velocities, and this communicates between the mechanical energy and internal energy. For example, it will eventually contribute to friction losses or friction heating, depending how you want to understand. So losing of mechanical energy and moving it to heat and so on. But we will dig to this a bit later. So to summarize the conservation laws, we will use the material derivative as a basic notation. So we have a conservation of mass, which is saying that the change of mass has something to do with the divergence of velocity. We have conservation of momentum. Conservation of angular momentum simply says that the stress tensor has to be symmetric. And conservation of energy in the form that we just discussed. So this is equation for symmetry of tensors. So it has basically several components on higher dimensions. This is a vectorial law. So in 2D it has 2 laws, 3D 3 laws. This is scalar and this is scalar, because density and internal energy are scalars. So ignoring the symmetry of tau, we have 2 plus n equations. So for 3D, it means 5 equations. And there are much more than 5 symbols here. So the conservation laws are not exactly enough to close the model fully. So, to reflect about conservation laws, first of all, this is not the whole truth. There are phenomena that we didn't take into account. For example, we didn't discuss anything about electromagnetism, which would bring a couple of more conservation laws to the play, and a lot of discussion how the electric energy will be moved to mechanical motions and so on, or to heating and so on. So there's a lot more to be dealt with, but that goes too far from the basic introduction. On the other hand, I guess we all are aware of theory of relativity and the fact that in relativity theory, mass and energy are interchangeable, so you can transfer mass to energy and vice versa, which means that actually there's no independent conservation of mass and conservation of energy. They are about the same thing, but it's a working approximation in many everyday uses. But this formalism, this set of conservation laws, doesn't apply to relative to cases where relativity, theory of relativity is of importance. So even if these are sort of solid physical theories, they are still theories. They are only valid in limited context. So they are only models that are approximately true, and they are approximately sufficiently true only in limited context. That has to be understood. They are models. They are not the absolute truth. Then, as we noted, we have less conservation laws than there are quantities that we have in the system. So the conservation laws alone don't explain everything. They don't dictate what is actually happening in the system. For any concrete system, concrete situation, we have to augment the conservation laws by other dependencies, other laws. And these are called material laws, and these are needed to build models that are closed and that can be solved, and that will sort of fully, again, whether they can fully model the system, but they lead to models that can be fully solved and results evaluated. On very general level, the material laws tell how the material reacts to the force, so how the stress tensor behaves, and how energy flows in the system. At least in these cases, when we don't take chemistry into account.